The graph with this shape is called concave upward. The tangent lines lie below the graph. The slopes of the tangent lines are increasing, meaning f prime prime of x, or the second derivative, is greater than or equal to 0. A graph with this shape is called concave downward. The tangent lines lie above the graph and the slopes are decreasing, meaning f prime prime of x, or our second derivative, is less than or equal to 0. A point on a graph is a point of inflection if the graph has a tangent line at that point, so differentiable, and the graph changes concavity. We go from concave up to concave down, or vice versa. The graph at right shows y equals x cubed, which has one point of inflection at 0, 0. Use the graph at the right to answer these questions. Base your answer on the appearances of the graph. On which intervals is the graph concave upward? We're looking for where are the tangent lines below the graph. This one has a slight curvature up, opening up, which means it's concave up. All these tangent lines would be below. Here I have it's opening downward, so it's a concave down interval where all my tangent lines lie above the graph. Here is a concave up interval where my tangent lines lie below the graph. Here is an interval of a line, so a line has no concavity. This one's opening upward again, so concave up, where our tangent lines are below, and this one is curving downward, so our tangent lines are above. And then from 6 to 7, we also have a horizontal line, in case you can't see that there. Use this information to fill in your answers for 1 to 4, and then check to make sure they're correct. We only have 2 points of inflection. Here the concavity changes at the point -1, 1, but there is no tangent line because this is a sharp turn. Analytically, we can find concavity intervals and points of inflection by using a second derivative number line. The procedure is parallel to the procedure used in the last lesson to find increasing and decreasing intervals, and relative extrema by using a first derivative number line. Determine the points of inflection and discuss the concavity for this graph. First, we're going to check for any domain restrictions. This is a polynomial, so the domain is -infinity to infinity. Time to derive. Find the second derivative. And now we're going to find possible points of inflection. Those are x values for which f prime prime of x is equal to 0 or undefined. Because the second derivative is a parabola, we do not have any domain restrictions. Let's factor and solve f prime prime of x equal to 0. We have 2 possible points of inflection, x equals 1/2 and x equals -1. Let's make an f prime prime number line and check the signs on each of these intervals. To the left of -1, in between -1 and 1/2, and to the right of 1/2. The second derivative is positive from -infinity to -1 and from 1/2 to infinity. So the graph of f is concave up on those intervals. F prime prime of x is negative between -1 and 1/2. So the graph of f is concave down on this interval. All right, once you've determined your intervals of concavity, you can take a look at those x values that were possible points of inflection before and decide if they are points of inflection. Remember, for points of inflection, the first derivative exists and the graph changes concavity, or the second derivative changes sign. That means -1 and 1/2 are both x values of points of inflection. To find the y values, I'll plug into the original function. And there's your answer. To determine the intervals of concavity and possible or points of inflection, we first need to determine if there are any domain restrictions to our original function. Domain restrictions would be anything that makes this denominator equal to 0. We have a vertical asymptote at -2 and at +2, so 2 vertical asymptotes. They've given us the second derivative, so now we just need to find where is that equal to 0 or where is it undefined. As a rational function, f prime prime of x will be equal to 0 when the numerator is equal to 0. Where the second derivative is undefined is wherever that denominator is equal to 0. Let's solve. If you notice, you're going to get x squared is equal to a negative, so that only gives you imaginary solutions. So there are no solutions, no x values that make the numerator equal to 0. Hey, this is just like when we were solving for those vertical asymptotes. So guess what? X is equal to plus or minus 2, but plus or minus 2 cannot be possible points of inflection because it's already vertical asymptotes. Make that f prime prime number line. As a reminder, -2 and +2 are not possibilities for points of inflection. They are domain restrictions. Time to test your science. I chose bigger numbers because I thought it would actually be easier. So -10 and +10. F prime prime has a positive interval here, making f concave up. F prime prime is negative here, which means f is concave down. The second derivative is positive here, which means f is concave up. Concave up on -infinity to -2, 2 to infinity. Concave down from -2 to 2. And we have no points of inflection because there were no x values for which the second derivative was equal to 0 or undefined. The concavity changes on either side of these vertical asymptotes, but as a reminder, they're vertical asymptotes, so they definitely can't be points of inflection because there are domain restrictions. The second derivative test for relative extrema. This uses the second derivative to help us evaluate if critical numbers are indeed local maxima or minima. We use f prime to find those critical numbers, and then we plug into f prime prime to analyze the concavity and determine whether the function has a relative max or min there. If you have a critical number and your function is concave down at that critical number, what does that give you? A local maximum. And if you're concave up at a critical number, that would give you a local minimum. The second derivative test does not always give an answer. So when f prime prime of x is equal to 0, the second derivative test is inconclusive. So only use the second derivative test when the directions require it or when the given information requires it, meaning maybe they haven't given you the function, they've just given you select values. First, find critical numbers. Are there any domain restrictions? No, this is a polynomial, so I can begin deriving. Critical numbers occur when the derivative is equal to 0 or when it's undefined. Here it's not undefined because it's a polynomial, so let's just factor and solve, make it equal to 0. So we have three critical numbers, x equals 0, x equals -1, and x equals +1. We don't need to make a number line, but we do need to find the second derivative. Then plug in your critical numbers to evaluate the concavity at each. Because the second derivative is negative at the critical number -1, that means we are concave down at -1. And if you're concave down at a critical number, then you have a relative maximum. Same with the critical number 1. When the second derivative is positive, or when the graph is concave up at a critical number, then you have a relative minimum. The instructions asked us for the relative minimum and maximum points.
So we're going to plug these critical numbers into the original function in order to find the y values. And there are our relative extrema. For number 8, g of x is a function such that, and then they give us a bunch of first derivative and second derivative values, but we don't actually have a function. So given these values, we're going to find the x values of the relative max and relative min values if and when possible. Let's write out all the information that we have. So the first thing to establish is that -3, -1, 0, and 2 are critical numbers because the first derivative at those values is 0. Let's look at the second derivative of those values to determine the concavity. At -3, we're concave up. Concave up indicates a relative min. Concave down, which represents a relative max. But when the second derivative gives us 0, that doesn't tell us the concavity, and therefore the second derivative test for relative extrema is inconclusive. Now they gave me the second derivative at 1, but they didn't tell me that 1 was a critical number. So if it's not a critical number, then it's definitely not an x value for a relative extrema. And at x equals 2, this critical number, we're concave up, so there's a relative min there. We've been given no g function, so we don't need to find the y values. So our x values for the relative max is -1, and the x values for relative minima, -3 and 2.